Thank you. So today what we're going to discuss is MLOps, but more in the areas of deep learning than in machine learning. We also have Guy with us. Guy has lots of experience in deep learning, also practical one from his previous company. And what we're going to talk about is how to build how to productize deep learning pipelines and using MLOps and different technologies which are open source. So first, the real challenge before we dive into the solution is that most organizations have really hard time moving from the research environment where things are relatively interactive and manual into production environments where things keep on flowing, lots of data, you need to do things at scale and so on. So we're going to show you how you can easily move from research areas to production areas in this session. Some people still think that they could take whatever they've done in the notebook and productize it. So it's not the case. We're not going to show how you essentially just keep your notebook and make it productized, but we're going to show you how you can easily bridge the gap between what you're developing in your sort of research environment and how to move it to production environment with sort of minimal efforts. Because you have to build something which is more of a service than something interactive like a notebook and a piece of code. And really, we need to change mindset because usually in machine learning, deep learning, AI in general, the mindset is developing things in research. So taking data, whether it's images or text and so on, in a data lake, object store, data warehouse, and so on, running some sort of preparation on that, running training, building a model, evaluating. And that is usually a very interactive circle. And then maybe we have a model, we take this model and throw it to someone else to build a complete application. But this thing is really hard if you want to keep on building machine learning projects, because a real project would look something more like that. We don't only train models, we train models so we can use models in production applications, in real-time applications. We also need to monitor every activity. We need to generate data, whether it's, again, video feeds or cameras or textual data or structured data. And we need to process that data so it will be usable for our model. So all those things, even training, we don't do that training in production interactively. We want to run jobs with GPUs at scale, etc., to crunch lots of data. So this is something that we have to move from a mindset of working interactively to working on top of dynamic infrastructure, building containers, building things that are fully managed services, etc. That usually takes huge amount of resources, engineering people, ML engineers, software developers, DevOps, data scientists, and so on. And one of the key challenges is also because it's a siloed process where the data processing is in one team and training is done on a different team, and building the actual production pipelines or real-time pipelines is a separate team, and so on. This makes things very cumbersome, very long, and very tedious. So we're going to see how we want to change the mindset from something very fragmented to have a more holistic build of our MLOps or our production pipeline, using essentially one tool that knows how to orchestrate the different tools that you're going to use throughout the pipeline. So this is an open source project called MLRun that we maintain. But it's open source, used by a bunch of guys, and it has 4 key components. The first component is about the feature engineering, and features, again, not necessarily structured data. We're going to speak about it in a minute, but also unstructured data and textual data. So first thing we want to do is build the data that is going to be used for our training. So we need to massage the data, pre-process it, transform it, and so on. Then we want to run the training in more of a continuous development and integration flow. So meaning fully automated workflows where we take a snapshot of the data, create versions of that data, run different steps in a pipeline like training, testing, compressing, deploying, and so on of the models. And then we have a model. And not just the model, we also have lots of metadata about that model, artifacts, charts, comparisons, information about accuracy and so on. So we have all that metadata that's being generated, needs to be logged and versioned. We're going to see how we're doing that. But once we have that model, we need to build a real-time pipeline. Real-time pipelines in deep learning especially are very complicated. If we're taking things like NLP or image processing, we have multi-stage pipelines involved, data pre-processing, inferencing, monitoring, anomaly detection, and so on. Those could be relatively complex pipelines. It's not just the model serving. People think that, you know what, in real time we just do model serving, someone else will deal with all the rest. But that someone else usually is not just standing by for work. We need to look at things in a more holistic way. We also need to think about versioning. If we version the model, we also have to version the pre-processing code. This is why we need a more holistic view of how we build the production pipelines. So we're going to see a few demos, NLP and image processing, that essentially use real-time pipelines for this processing. And finally, once we served an application, we have to collect a lot of telemetry on that application, on its behavior, identify anomalies, problems with the model accuracy, drift. We want to also measure the impact of our application on business. Let's assume we build a recommendation engine. It's not enough to say, you know, our model is accurate. We want to measure, is that recommendation leading to new business? So we don't just monitor the application, sort of the model itself, you know, its accuracy. We have to model to also monitor information that will lead for calculation of really, is there an ROI for that model? Or maybe there are different ways that we can sort of take the model inferencing decision and create different actions that will lead to different business impact. So those are things that people are now looking into more and more, to measure not just the impact of the accuracy, but also the impact on the business. So this is really where the production pipeline lies. But production pipeline is usually the end after we've done some interactive work and development and research. So there is essentially a need to form sort of connectivity or SDKs or APIs between the different tools that are sort of above and the layer underneath of the real or the production pipeline. So we need tools like notebooks or exploration or labeling tools or CI frameworks, Git frameworks, and so on. And we need those to interact directly with our production pipeline. And we're going to see how we're going to do all those things. So essentially, what we want to look at, it's not just, you know, taking a piece of code and saying, okay, we're going to serve a model or we're going to run some training. When we move from development to production, we have to think about all those things that you see here in the slides. You know, we have to take a piece of code and know how to package it in containers with parameters and scripting, and, you know, record all the package versions. We want to run some unit testing on it. Then when we build it, we want to scale it out. You know, we want to train a large model. We can't just train it on a single VM or a container. We have to scale it out. So we have to think about different strategies of how to partition our workload. And every type of workload has a different way of scaling it out. You know, if it's data, structured data, we usually do things like shuffling. If it's sort of models, we may want to distribute our model. We may want to run different parameters on different containers, like when we're doing hyperparameter search, etc. So there are different ways to create horizontal scaling of our workload. We also want to make things very efficient, so we have to tune our workloads. Maybe we want to add GPUs because they provide acceleration. We're working against data. Maybe we want to apply caching tricks, or if we're working against databases, maybe we want to tune our queries to make be able to do a lot more IOs for the same cost and latency. All of those considerations are considerations that you have to take into production. When you're building production, those are not trivial things for people that are data scientists, because they didn't build, you know, CI systems and query optimization systems and so on. So we have to have a bunch of different people and different disciplines that build all of those things. On the operational side, we have to instrument also everything that we do. We want monitoring and logging and troubleshooting and versioning and security hardening and all those, so we can really push something into an enterprise application. So who's going to do that? Is that the data scientists? Probably not. That's probably more in the areas of ML engineers or DevOps. And we also need to automate the entire workflow, because every time we change a piece of code or data or some logic, we want to be able to automatically run all the integration tests, compile, build, etc., instead of doing that manually again and again. So we have to do all of those things, and this is really the hard problem. Not, developing a model takes time, but operationalizing a full application that involves model, data processing, and so on is a very long process. And what we're going to see is how we're going to shorten this process dramatically. So the traditional approach, one of the caveats is also that things are very siloed. There's a data scientist developing something in Jupyter or PyCharm or something, and then someone else takes that code and builds a container out of it that runs on Kubernetes and potentially running on GPUs and so on. And then when we want to build a full application, it's not just one container, it's probably multiple stages and different things. So someone else assemble all of those and also do the integrated data engineering, all the aspects of fetching data, processing data, storing data, versioning data. So moving from a container to sort of a full workflow, that's a lot of headache, which is usually done by other people. And then you want to collect enough telemetry to be able to understand what's going on every stage of the application. That's a lot of extra work of instrumenting each part of your pipeline. And sometimes that's done by other people that are focused on monitoring. And because they're not monitoring at the application level, it's not as valuable data as if you would monitor things from the application perspective. So we want to break those silos and complexity. So this is essentially what we're trying to do with MLRun. So everything is automated. So the move from writing a piece of code in the notebook or your IDE into a fully working service running on Kubernetes is usually a single line of code. And Guy is going to show that in the demo. And also working with all those other things that we discussed, auto scaling, logging, monitoring, GPU integration, checkpointing, and so all those things are done automatically without a single line of code from the developer. And we're going to see that in the works in a minute. Logging, versioning, tracking, all that. Now, as we build something more comprehensive, which is multi-stage, and we have the training code, we have the testing code, we have some real-time pipeline code. We want to assemble something that starts with fetching data or with pushing data and ends with like a business impact, something that interacts with the user, throws an alert, and so on. So building that entire pipeline, it can also be automated. And finally, because the instrumentation is buried in all those automation tools, in the model services, in the data processing services, etc., you're tracking everything at the application level. And when you're tracking everything at the application level and automatically, because you're collecting lots of data, you can use it to provide feedback and, for example, redeploy a model after doing some retraining, or tweaking an ensemble, or providing feedback to the user that's developing a model from the production side on the data behavior, on statistics, that you can tweak and change his model to meet the business goals better, or measuring the impact of the business on the business side from this application, or actually running multiple flows in parallel and doing sort of A/B testing, feeding that A/B testing results into the developers so they can make changes to their models. So those are things that could be automated if you choose that approach. And one of their core capabilities allowing us all those goodies is serverless computing. So serverless goes beyond containers. It's essentially, think of it as taking a piece of code and someone else takes that piece of code and turns it into a service. It started with things like Amazon Lambda and so on, but for those kind of workloads, which are very heavyweight, require GPUs, heavy processing, we need something else. And this is really where MLRun packs a bunch of technologies to be able to do distributed computing using sort of serverless approaches. It has actually different runtime engines. For example, for deep learning, it knows how it builds serverless functions around something called Horvath, and Guy is going to show us that, which is distributed horizontally across multiple nodes. For other workloads like data processing, it can orchestrate Task or Spark. For real-time serving and real-time pipeline, it's using a very powerful engine called Nucleo. We're going to see that in action. And what those serverless functions do, they take your code, they turn it into an horizontal scaling piece of service, and all the tracking, everything is built in to that piece of code. If you want to read more, then you can go into the MLRun documentation on that part. So MLRun essentially provides you 4 key services. One is the feature store. That one is building the real-time serving pipelines, and we're going to see a few examples of those. The ability to monitor, track, and trigger retraining and things like that. And finally, a full automation for all your development process. Starting with the first feature is the feature store, which is essentially an ability to bringing data from different sources, could be structured or unstructured, being able to transform it into something more meaningful that's going to be used by our application, cataloging all this data in a version catalog. So if we want to train, we can choose different versions of data, we can select what we want to train on, and so on. And also being able to save it, to serve it in real time for more real-time use cases. So that's essentially the feature store. MLRun feature store is, I think, the only one that supports not only structured data, but also unstructured data. And it can interact with many different tools around it. So on one end, APIs for data labeling, data exploration, notebooks for interactive development, building snapshots of data for the training, real-time serving, and the monitoring aspects. Now, when I'm saying structured and unstructured, so essentially with the MLRun capabilities of sort of graph computation on top of those serverless functions, you can do a bunch of different transformations. You can take a piece of data coming from a source. A source could be an HTTP endpoint that you generate, a Kafka stream, a video stream, a database, an S3 bucket, and so on, and run a bunch of transformations. So because it's so flexible, there are some streaming technologies like Apache Flink and Beam, etc., but they're very focused on structured data. What we've done with MLRun, it's very Pythonic, so it's very native to use it if you're writing Python. It's not based on Java. And also it can do any transformation you'd like. So we're looking into the different types of data, structured, textual, visual, even composite. There was a great session from IHS Markit on how they're using MLRun serving graphs to run essentially process documents, which have composite data, visual, tabular, and textual, all in a single document. So you have all those different transformations that you want to build in order to build sort of the features or the application that uses those features. So that's the first thing. The second thing that we talked about is building automation around all the training and the development of the model. So what we want to do is build an automated flow where every time we have a new piece of code, or we change parameter, or every time we have a new data set, or just refresh the data set. Maybe we have a bunch of new images and they're unlabeled, and now we label them and we want to train on those new images. So every time we have a change in the data or the code and parameters, we want to run a flow. And this is a relatively simple flow of training, testing. We see more and more need for optimization. Guy is going to show us how he's using Onyx optimization to improve the performance of a deep learning model, and then deploying that a pipeline into a staging cluster or a production cluster. So we want to build a full automation, but automation is not just about running the different steps in the pipeline. It's also about integrating with the different other systems, like with GitHub and GitLab, reporting everything to tools like TensorBoard without necessarily having to write additional piece of code, orchestrating the pipeline using different tools like Kubeflow or GitHub Actions or Jenkins and so on. So all those things are supported automatically by MLRun. You don't need to write the code for logging into TensorBoard. You're going to see a nice demo in a minute. And if you want to integrate that every time you push a pull request in your GitHub, you can automatically run a full automated pipeline for building your models just off of this trigger of a pull request. Ping us if you need more information, but we have demos for all of those things. All those things are covered in the MLRun.org documentation site. Now, it's not just about being able to automate, it's also about being able to control the resources, which is very important, especially if you're using GPUs. So MLRun knows how to orchestrate different types of instances and spot instances to lower cost. When you're running a job, you can specify the amount of resources you want, like GPUs, CPUs. You can even give it tolerance. You could say, between 2 and 4. So if there's no load, it's going to shrink down. But when you're starting to have load, it will start adding more and more computation resources. And you could see this, the consumption of computation resources mapped to applications, projects, services, and so on the dashboards, including aggregated information about the usage and utilization of resources. So everything you do is automatically tracked without writing a single line of extra code. Moving to the real-time pipeline, what we said, we need to compose a graph of computation. This one is relatively simple of machine learning. We want to push in some events. We want to enrich the data, maybe do some pre-processing, build an ensemble and some post-processing. Building that, usually the data scientist only builds sort of the model, and someone else builds the rest of the system. And then they go and starting to integrate, and there's a mismatch, or someone changes his part and it impacts the other part. So here you're essentially building it as one flow. Only a few lines of code. There's lots of examples on that, and we're going to see some in a minute. So you can build it with a few dozen lines of code. You can test it using a simulator in your notebook or ID environment or PyCharm. Once you see that it's working, you just say deploy, and all that pipeline is going to be deployed on serverless functions in production or in a test cluster. And that could also be integrated with the CI system. Another interesting thing which the MLRun graph support is distributing that workload on top of multiple containers. And that's very important for deep learning workloads, because usually deep learning workloads are very optimal for GPU. But in many cases, you also need to pre-process some data, resize images or fetch images from object store, break frames from a video frame and so from a video feed and so on. So doing that on a node with GPU is very wasteful. You're not going to fully utilize the GPUs. You're going to wait on I/O and all of that. So you may want to distribute your workload where some of the steps in the computation graph are running on one container without GPU, and some other steps may run on containers with GPU. And by the way, each one of those is elastic. So if we're going to use more TensorFlow and we'll need more GPUs, specifically step number 3 is going to scale, while maybe step 1 and 2 are not going to scale because they don't need more computation. So that's again a very powerful feature. There was again this IHS presentation where they showed how much money it saved them moving to this approach. And all of that can also run over spot instances, which are 50% the cost compared to regular instances. So that's on that. And finally, there is model monitoring. Again, everything could be monitored. There is a good question: how do you monitor drift of a deep learning? That's probably a topic for another session. But again, if you're trying to do that, talk to us. We'll help you with that. So people that are starting to use that technology, and they can lead to significant impact on those technology, on those applications. So this is an example of one of our users, H2I in Singapore. And what they're using is essentially they're doing analysis of images to identify, rainfall, and essentially doing that over using CCTVs, and based on that, they can optimize the usage of water in Singapore. So Singapore doesn't have lots of water, fresh water, and this improves the utilization of the water. They can make use of rainfall much better way. So this is using this technology of essentially collecting data from CCTVs, analyzing the images, and based on that, making a forecast, and this way they don't have floods, and they're using all the waters instead of flooding them into the sea. So that's an example of an application. Some other applications that there are full demos that you can see in those links in GitHub. This is a nice demo of a real-time news processing pipeline. So essentially fetching articles, doing all sorts of transformations on those articles, and indexing all the information in a database. I won't dive into that today because you can just look into the Git. Another interesting demo in the Git is also NLP using processing structured and textual data in the same demo. So we can train a BERT model, save it in the model store, and then what we have in that demo is feeding real-time information from Yahoo Finance, both market news, so textual data, and stock ticker, essentially time series data, and feeding that both those data elements into the feature store, and also using the BERT model and embeddings to do the inferencing, and also analyzing it using other tools. But again, I'm not going to dive into the demo. You can see the full code in that link here. The last demo that essentially Guy is going to go over something very similar is Guy is going to show mask detection, but this is actually being used in like manufacturing for looking into images and classifying bad parts and so on. So usually how it will work in a production environment is we have all those images or video feeds that are coming in, and they're stored on an object storage or a file system. If it's a video stream, we usually cut it to individual frames, and we throw it into objects or file system. We also may maintain some notifications in a stream, so we know every time there's a new update of an image. Once we throw all the data into that repository, we need to run the training pipeline, which may comprise of taking the images, running TensorFlow. We want to do it horizontally, scaling using Horvath, so that will be done automatically for you using MLRun. It will know how to distribute your TensorFlow or PyTorch code over multiple GPUs, and potentially you can even use hyperparameters. You can play with the parameters, and it will distribute that on the cluster. Once you have it, then you may run some test and validation, or optimize your model to compress the models and improve the performance, which from our measurement, Onyx improves quite a bit the performance of the models. And then we need to deploy the models. But everything you see here is only the development. It's only the CI part. It's not the real-time pipeline. So another thing that you have is the real-time pipeline. When we click deploy, we essentially will create the full production pipeline, which needs to go and fetch the images and do all sorts of processing on the images and classify the images using a GPU probably, and then store the results, push the results to some message queue. So this is an example, and the mask demo that Guy is going to show us follows that pattern. So handing it over to you, Guy, and if you want to talk about this slide, add some more details. And
no, it's okay. I can start with the demo.
Go for it.
Okay, so do you see my Jupyter?
Yes.
Excellent. So, like Yaron said, in this demo, we will showcase how we train a model to classify whether the person is wearing a COVID mask or not. and we will build a serving graph and an automatic pipeline, and all of this using MLRun to orchestrate the process. We will use TF Keras to train the model. We will use Horvod, which is a distributed training framework to distribute the training. And we will use Onyx to optimize our model and make it run faster. First, the dataset is by, I hope I will pronounce her name right, Prainia Baadari. She made a dataset of images with or without masks. So this is what we will use in the demo. And the training code we are using is from PyImageSearch that uses Prainia dataset. The prime example is that we took a code that we did not write, and with very simple tweaks, MLRun is wrapping it and enabling auto-logging, distributed training, serving. So let's start. Let's go up. Okay, so first we want to train our model. So here we will set a project with MLRun create project. And then the first thing we want to do is to download the data. To download the data, we use MLRun's function marketplace. The function marketplace is essentially some common and generic functions that you can just import to your project, whether to do a concept brief, for example, aggregate, and in our example, download a zip and extract the contents of the zip to a local directory. So I am using the import function from MLRun to get the function. The function is called Open Archive. Here you can see I'm writing .doc to import the documentation. I can see how to use it, what parameters it gets. And now we will run the function. So in order to run the function, we simply use our function object, call run, give the inputs and the parameters to run the function. And you can see here the flag local is true, meaning I am running it on top of my Jupyter interpreter. So you can see here that I got the data set. Let's see it with mask. And here you can see an example of a person with mask. So moving forward, now we are required to select our framework. We will use TensorFlow Keras. PyTorch is there as well. Here is an explanation of the code, but let's jump to the code and we will see it in action. So this is our Py file with the train function. The training code is very straightforward. We just use this function to get our data sets. We have a training and validation set. Get model is initializing our model. The model is based on a transfer learning technique from MobileNet v2. And let's ignore this for a second. We are initializing an optimizer. We call compile and we call fit to train the model. So far, nothing is out of the ordinary, but this function. So apply MLRun is our way of injecting and wrapping the model with MLRun features, so we can control it using MLRun function outside the scope of this simple Python file. And with this single line of code, we will gain distributed training and we will gain auto-logging, which are both very configurable. Here we're just using the default setting. So going back to our notebook, let's create the function. We will use MLRun code to function which is taking either a Jupyter notebook or a Python file. So you can see training and evaluation file. This is what I'm giving it. I'm giving it the image that I want to use and the type of job I want to use for the function. And then all I need to do is just hit run. We will notice now the local flag is false, so we will deploy a pod and run training on top of it. And now you can see I'm using.
Just to clarify, deploying a pod means like
yes,
the code here will run on a Kubernetes cluster without adding any extra work. This will MLRun will automatically take your code, package it, send it, build containers, all of that, run it on the Kubernetes cluster, and even provide you the console back as if it's running locally.
Yeah, so here you can see the logs. Again, it's ordinary stuff. Here the summary of our training run. You can see here artifacts that we generated and our model that was logged as well. Let's click here and we will see our training function. So here I can see my function. Here are the pods. When it was running, you would see the actual pod, the train. You can see the logs that were shown in the Jupyter. We can see the result that all these results are automatically tracked. So loss, accuracy, learning rate. And you can see some artifacts, for example, accuracy summary.
Yeah, just again to note, there is not even a single line of code in the TensorFlow that is asking for those charts. All those charts are essentially generated automatically for you.
Yeah, this is all done by apply MLRun. So you can have all your cool stuff. And if you like TensorBoard, it is also logging into TensorBoard as well. Here you can see the logs. I have my learning rate being tracked. I have my training accuracy, training loss per batch. This is per epoch. And I can also as well do hyperparameter tuning with parallel coordinates here, which is something that it's not coming like freely with the TensorBoard callback. It's actually a little bit more complicated to do, and apply MLRun is doing everything for you. Here you can see I can click this and I can see the run that yielded these results.
And just again to clarify that every time you will rerun the job, it will record it again, and then you can compare across different runs.
Yeah, exactly. So we support for TensorBoard everything for weight histogram. It's not being logged by default. This is why you don't see it here, but everything the original TensorBoard has, this has as well. So let's move on.
And also we have, there's also profiling, because some of the things that we've seen, a lot of people want to understand. Can you expand about profiling?
Yeah, so TensorBoard has also a profiler, so you can know what took more time and GPU utilization in your model. So it's a very cool and visual way to debug your model and see where it have a lot of time in work inside the model. So this is the training. We train our model, we have it as well, and now we want to run evaluation. So in order to run the evaluation, I'm taking the training run. If you missed it, this is the object that came back from the training function. So the evaluation function needs a model. So all I need to do is just hit outputs and give it the mask detector, which is the name of the mask artifact you can see here. and it will just take the model and run an evaluation on it. So you can see here all the evaluation metrics as well are logged and being saved to the model artifact. So the last thing in this notebook is to use Horovod to distribute the training. Horovod is basically split the training to workers, and each worker is inferring the data, and when it's propagating the gradients, it will do an average of the gradients, and the average will update the weights. So enabling Horovod is also not a light-headed task, and logging Horovod is also a bit tricky. But again, the apply MLRun is doing everything, and I can also log Horovod as well. You can see the Horovod run here, and you can see it.
Also, you can specify as you've shown there, the resources like GPU, number of nodes, etc. Just as a parameter.
Oh, yeah. So in this example, I'm doing 2 workers. So I'm setting 2 replicas, and if the use GPU is set to true, it will just give 1 GPU to each worker. Otherwise, it will use simply just 2 CPUs, and then it will run on using these 2 workers. So you can see this run in TensorBoard. You can see it is the blue run because it is half the steps. And why? Because half the steps is done by each worker, and only the average is logged. So this is why you can see the run was smaller, but it ran on all the data as the same as the orange one. Okay, so we finished training our model. We have a model in our hand. Let's see it in MLRun. So this is my project, mask detection, and I can see all of my functions that I ran, and as well I can see the model here. So every model I logged, I will see here. The Onyx Max detector we will talk about shortly, but this is the model we basically just logged. We can see the version, and I can also see all the artifacts that are logged with it. So all the metrics and accuracies are always right by the model artifact. So it will be easy to see what kind of model is it. Is it the best model, and so on. Okay, so now let's talk about serving. So in this example, we will build a serving graph that will take a simple URL. It will download the image, it will resize it, it will apply pre-processing that is required by MobileNet, and then we will infer it and post-process the data before we return. So again, we just set up the project to our project from training, the mask detection. We are choosing the serving code to be TensorFlow Keras. And here we are just doing the code to function on our serving. So the serving is just like Yaron said, it is just simple Python code, no tricks, no shticks. You can see here that I have my resize function, which is just retrieving the URL, open it, resize, and then append it to a list. I have my pre-process. I'm using the Keras application MobileNet pre-processing, wrapping it, and I have my post-processing that is just simply squeezing the output and giving it a neat response. And all of that, each of these functions will be a step in my graph, and you can see it right here. So I have my resize, I have my pre-process. Detect mask is the mask detection, is the model itself. And I have my post-processing that will be my final answer in the serving graph. Building it is very simple. It's the code you see here. Basically, you can ignore this because this is the class of the model server we want to use. So for TF Keras, I'm using the TF Keras model server. For PyTorch, I'm using PyTorch model server. I'm just giving my serving function a topology, and then I'm inserting into this topology steps. So I'm having my resize, then it is going to pre-process, then it is going to a model server, which is getting my mask detector artifact, you can see here, and then it is going to pre-process, which will respond. So let's test our serving graph. Here you can see I'm just declaring my classes, declaring this is the image URL I will use. You will see them shortly. And this is just a function that I use to print the image and the classification. So in order to debug our serving graph locally, I will use a mock server. So it's very simple, just serving function and then .to mock server will deploy me locally. And you can see here, I use the print image classification, gave it the image URL at the place 0, and our model is classified as with mask. We are very happy. And again, with the second image, without mask. I am happy with my serving graph, and I want to deploy it. So all I need to do is just call deploy. This will deploy the function. You can see all the stages here. And once it is done, it is giving me the HTTP endpoint, and I can just send it to its request, and it will answer the same as we saw back there. So again, the first image and the second image. So we'll continue to the automatic pipeline. In this notebook, we will build an automatic pipeline that will download the data set. We will go to train. We will build an image with Onyx packages. We will optimize our model using Onyx, and then we will deploy the Onyx model as an HTTP endpoint. Also, we will run evaluation post-training, just to enrich the pipeline. So just the same as before, we set a project to our mask detection. We are setting the framework to TensorFlow Keras, and then I'm going into the project and I'm setting a function. I'm taking my training and evaluation Python file and my serving Python file. And now I will import from the marketplace. I will import the Open Archive and another function called Onyx Utils. And now we will write the pipeline workflow. So the workflow is very straightforward. Well, you don't have to do such huge headers, but it helps to know what step you are writing. We have the build Onyx image. It's just an MLRun.build function. We are giving it the function name that we register to the project. We're giving it a base image, and then we're giving it the Onyx requirements. So these are the Onyx requirements: Onyx runtime, Onyx ML tools, TF2 Onyx, all of the good stuff. Then we will download the dataset. So we got project get function, and then we will run the function. We will train the model. It's the same stuff as before. And here we will convert our model to Onyx. We will evaluate the model, and here we will deploy our serving graph just as before. The only difference is we will use Onyx model server because now we have an Onyx model. So very easily, I just trained TensorFlow, optimize it using Onyx, and serve an Onyx model with very little effort. And when I done with the workflow file, I will set it to the project. I will hit save, and then I just run the project. So running the project will have like a kind of neat graph that will turn green every time it is done with a step. So you can see here I have my open archive, I have my deploy Onyx, which is building the image. The Onyx utility is using this image and the model from training. And then we deploy with the model that is the output of the Onyx utils. And
maybe another point, Guy, is that essentially what we're using in this case is Kubeflow. So MLRun is creating a Kubeflow pipeline, if you're familiar with Kubeflow. There are also other options of using GitHub Actions or Jenkins or other things to run the workflow as well. But this is like we built what the workflow code is, just stitching the different steps together, the different tasks together, like what gets the output of the previous step and moving to the next step. And then there is the thing that runs the pipeline. In this case, we're using Kubeflow engine as the workflow runner.
And well, that's it. Here you can see all the functions that we ran. And if we want to test the Onyx model we just trained, so here we can see I'm accessing it using the same print image classification function, and I'm having excellent classification with both images.
Yeah, and another point is moving this to an automated CI is trivial, because once you save the project, you can essentially run this inside the Git pull request. There's also, I think there is a node there above, a guy on that, but you can find it in the MLRun documentation.
Yeah, so this is
you can export the project, and then you can take a different cluster or run it within your CI system. Every time you change your code, it will automatically run this workflow.
That was a mass detection demo.